Action potential has everything to do with one property of the muscular system, excitability. In other words, its ability to respond to stimulus. This is huge. Now, the setup for this, or what makes this possible, is the sodium-potassium pump. You should remember the basics of the sodium-potassium pump from biology. If you don't, I want to say it's chapter 3, the first part of chapter 3, no, chapter 2. The first part of chapter 2 discusses this idea. This figure is in fact taken from chapter 2. It's worth studying and reviewing and making sure you understand what's behind it. The point of the sodium-potassium pump is that it's what makes possible the ability to respond to stimulus. It revolves around active transport, which basically means it requires tons of ATP. So the sodium-potassium pump is actually one of the reasons that a lot of ATP is required for both the muscular system and the nervous system. It's one of the reasons they're huge energy hogs. Now, how it does this is, notice our setup here, sodium, potassium. Basically, the sarcolemma, which is our specialized plasma membrane within a muscle cell, a muscle fiber, just like any membrane, it's impermeable to ions. So anything with a charge cannot get across the membrane. So because of this, you can create areas of concentration because we can prevent the transfer back by simple diffusion across the membrane. So notice that I end up with a high concentration of sodium outside and potassium inside. Again, remember the sodium-potassium pump moves sodium out and moves potassium in. It takes energy because we're working against the gradient, we're working against diffusion. And so because you're working against it, energy is required. The important thing to note here is that it creates the chemical gradient. Okay, this is very important to the next process. The second component, or the second effect of the sodium-potassium pump, is the electrical gradient. And this is, for lack of a better word, a relative gradient, simply because more sodium is pumped out than potassium is pumped in. So you'll notice on these diagrams that we have the positives to the outside and the negatives on the inside. Now here's the kicker. If I have a resting membrane potential where I have a chemical and an electrical gradient created by the sodium and the potassium, disruption of this electrochemical gradient is what leads to what we call an action potential. Now, to set this up, requires the release of ACH, which is also known as acetylcholine. Now, what's cool about acetylcholine is it actually has to diffuse across. We have a gap here. This is the synapse. It has to diffuse across the synapse and it binds to protein receptors. What you again, something else you should remember from biology is that anytime you bind to a receptor in a membrane, you have the capacity to change the performance of the membrane. This is especially true when we talk about acetylcholine and something that is excitable like the sarcolemma or a neuron. It literally will change how the membrane behaves. Okay, so let's back up. These receptors are basically proteins. The proteins are what serve as a channel for ions or such to be able to get across. So what happens is the binding of that protein opens these channels. Okay, new term here that you want to kind of put in perspective. What's known as gated channels, voltage regulated channels. Now, what the gated and the voltage regulated has to do with is that idea of the electrochemical gradient. The electro gradient is this idea of membrane potential, and that I actually have, remember we said we had that relative charge, I actually have the ability to conduct electricity because I change how the positives and the negatives interact. In other words, when I open this sodium channel, because I have now changed the internal charge. So remember that the inside of the cell was negative. So as I open those channels, when acetylcholine binds and opens the channels, sodium can suddenly diffuse in. Okay, so as soon as the sodium can diffuse in, that means it's going to disrupt this positive and negative that we have. Because now I have all of these positives being able to rush in. And that results in this change that begins to take place. I see it becoming less negative inside. This lessening of the negative, where the interior begins to become more positive, has a domino effect. And so more channels will open, more sodium can suddenly rush in, and so you'll notice here I have all of these negatives, all of these positives, and now I see this trigger, I see this domino effect as it moves through the plasma membrane. This domino effect, this change in the electrical current both inside and outside, is what is termed the action potential. So ultimately, when we talk about the action potential, that's what we're dealing with, is we're dealing with that change in the electrical charge. Now, more importantly, the change in the electrical also causes a change in our chemical gradient. In other words, what allows this is the fact that I have created a gradient in the first place, because there's excess sodium out and excess potassium in. Literally, as soon as I open that channel, the sodium's going to rush in, because normal diffusion is down a gradient. So if I create a steep enough gradient, sodium's going to rush in, and that rush in does this massive change inside and outside the cell. Now the other thing is to notice we have what's known as threshold. So I have to hit a certain point for the domino effect to take place. That certain point is threshold. As soon as I hit that, that domino effect happens, and I have this steep rise in the internal, okay, this is the internal charge, such that I go from negative inside the cell to positive inside the cell. And that's the point. That is the action potential. However, that's only the first half of the action potential. So again, as we talked about up here, we see that domino effect. We see this spread. Okay? So again, threshold is our minimum. Okay? It's the minimum change that has to happen to produce the electric current, because that's in essence what an action potential is it's the production of an electric current. Now, as soon as that happens, what's very cool is that once it starts, it's unstoppable. This is where we get the phrase all or nothing. Okay? You'll also see this apply to muscle contraction itself, all or none response. Basically, it's a zero sum. You either have contraction or you don't. You either have an action potential or you don't. So basically, if I add sodium here, but I never reach this threshold point, an action potential will never occur. We'll never get this peak that has to happen. Now, as soon as the depolarization occurs, and that's what we call it, is depolarization, the cell tries to reset. Because again, what's normal? Any component of the body is always trying to return to homeostasis. The electrochemical gradient is the normal status. It's the status quo. So as soon as we disrupt it with depolarization, it wants to return to the status quo. So to do that means I have to reset, at the very least, the electrical gradient. And that's what happens when we see, as soon as we hit that peak at 30, right here, okay, notice that the sodium channels now close and the potassium channels open. So again, we still see voltage-gated control of diffusion. So the voltage gate here was as soon as we started getting positive, the sodium channels open, we hit the peak. When we hit 30, that's the trigger for these to close, but now these guys open. And as soon as they open, now I have potassium rushing out of the cell, okay? And so the rushing of the potassium out of the cell helps to restore that electrical polarity, because now as the potassium rushes out, okay, I'm going to have more positives outside than inside. Keep in mind, what's the sodium potassium pump doing during all this? I mean, does it just shut down? Okay, so even though we have these massive openings, the sodium potassium pump is still doing its job. All right? As long as there's ATP available, you're going to see sodium removed from inside the cell to outside the cell. Let me get my pen here. 3 at a time. And you're going to see potassium moved back into the cell 2 at a time. So when those voltage-gated proteins open and this exchange is happening of the sodium and the potassium, we see the subsequent change in the charges here. We see this begin to drop, and as it drops, we hit our point here that we care about. We get below threshold. Notice how this drops a little lower, okay? And it's not until we hit the bottom here that we see the potassium channels close. And so when we hit the bottom, the potassium channels close. We hit a low enough negative, and then we see the sodium-potassium pump returning us back to the status quo, back to normal, back to that homeostatic level that is ready for another action potential. Notice the depolarization wave simply follows, our repolarization wave, our repolarization wave here follows the depolarization wave. We have that dip right here, which is known as latency. And basically that's the pause, shall we say, between the muscle being stimulated, the action potential being started. It has to go through, it's an all or none thing, so we literally have to go all the way through before we can have another one. Meaning we have to make through latency before another action potential can be triggered and we can stimulate everything again. And again, as we stated before, basically our normal resting potential is restored by the sodium-potassium pump, and that's what you see here as this drifts back up to the starting level. The main thing you want to do, folks, is link this picture to everything that we just talked about in terms of the sodium, in terms of action potential. So you want to recognize what's going on and what's required. The cool thing about this is its relationship to contraction. This is the physiological start of contraction. This is what allows anatomic contraction to occur. When we talk physiological contraction versus anatomical contraction, remember the anatomical is that actual shortening. The physiological is what actually permits the anatomical shortening to occur.